Good day everyone. Today I will discuss our laboratory activity 10 on digital signals. And Say transform, the main objective of this lab was to compute and visualize the Say transform of given discrete time signals, which is a fundamental tool in analyzing digital systems. We started by looking at the basic signals such as the unit impulse signal delta n, the unit step signal un, and the exponential signals r raised to n un, where r is a constant. Using Python and the SIMPy library, we are able to compute the symbolic Say transforms of these signals. For example, the Say transform of the unit impulse is simply 1, while the unit step and exponential signals have sums expressed in terms of Say raised to negative n, which allow us to analyze their behavior in the Say domain. Next, we visualize the signals using matplotlib. We plotted the unit step and the exponential signals to see how they behave in the time domain. The unit step remains at 1 for all non-negative n, while the exponential signal decays or grows depending on the value of r. This visualization is helpful because it allows us to connect the time domain representation to the behavior in the Say domain. We then explored the Say transform for a practical example using 0.5 raised to n un and calculated its inverse Say transform numerically. By plotting the inverse Say transform, we confirmed that the original time domain sequence is recovered, which demonstrates the consistency and the usefulness of the Say transform in analyzing discrete time signals. Finally, we analyzed the poles and zeros of the system, which are critical in determining stability for the system h Say equals 1 over 1 minus 0.5 Say raised to negative n. We identified a signal pole at Say equals 0.5 and no zeros. Since the pole lies inside the unit circle, the system is stable, meaning that a bounded input will produce a bounded output. This analysis also connects to real-world applications, such as digital filter design, signal processing, and control systems, where understanding poles, zeros, and the region of the convergence helps engineers design stable and efficient systems. In conclusion, the Say transform is a powerful tool for converting discrete time signals into the complex frequency domain, allowing us to analyze stability, frequency response, and growth characteristics. Visualizing these transforms with Python not only help us understand the theory but also demonstrates practical applications in engineering and digital signal processing.